You are about to hear a discussion of a first in the history of exploration. The most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space, the space between the stars. This conclusion is possible because of data from the spacecraft's plasma wave science instrument, built and operated by the University of Iowa and a team led by Don Gurnett. The 36-year-old probe is now sailing the uncharted waters of a new cosmic sea, and it has brought us along for the journey. Now let's talk about the details of this historic announcement.
Ladies and gentlemen, as you've just heard, today is a historic moment for NASA, the Voyager team, and in fact, humankind. My name is Dwayne Brown with NASA's Office of Communications. We have a lot to cover. We're going to get right into it, but a reminder that all of the information you will hear today and much more is on our website at www.nasa/Voyager. Join the conversation. A lot will be talked about today. Twitter, Facebook, and other social media venues. And join the Q&A session. Send in your question at #AskNASA. Before I introduce our panel, to give opening remarks, would you please welcome an astrophysicist, 5-time flown space shuttle astronaut, and head or associate administrator for NASA's Science Mission Directorate, ladies and gentlemen, Dr. John Grunsfeld.
Space, the final frontier. These are the voyages of the starship Voyager. Its 36-year mission to explore strange new worlds, to seek out anomalous cosmic rays and new plasmas, to boldly go where no probe has gone before. Those words from Star Trek, of course, have inspired so many of us, and I think are characteristic of the excitement and the discoveries we're going to talk about today. Voyager, like the ancient mariners, is pushing out into new territory. NASA science is all about exploring the Earth, the solar system, the galaxy, and the universe itself. Someday, humans will leave our cocoon in the solar system to explore beyond our home system. Voyager will have led the way. Today's exciting science results reflect a dynamic and, I suspect, continuing debate about the nature of our heliosphere. This story is a story of science, a story of exploration, and a narrative about over 40 years of hard work by one of our top teams of scientists and engineers. That's almost the entire history of the space age. I'd personally like to salute one member of the team, my former boss, Ed Stone, one of our country's greatest scientists, and my personal hero. And to Voyager, I say, live long and prosper.
Thank you, sir. Okay, now to our panel. First up, you will hear Ed Stone, Voyager project scientist, California Institute of Technology. Don Gurnett, Voyager plasma wave investigation principal investigator, University of Iowa. Gary Zank, Department of Space Sciences, Center for Space Plasma and Aeronautics Research, or CSPAR, at the University of Alabama in Huntsville. And Suzanne Dodd, Voyager Project Manager at NASA's Jet Propulsion Laboratory in Pasadena, California. And with that, Dr. Stone, I'll turn it over to you.
Okay. Well, this is the spacecraft, the first to interstellar space. We made it. Well, we still had enough power to send back home what it was that we are now exploring in this new region of space. 35 years, 13 billion miles journey It began in 1972 when the project started, July of 1972, with launching two spacecraft in 1977 for Jupiter, Saturn, Uranus, and Neptune. That was 1989. And then in 1990, we began what's now called the Voyager Interstellar mission. You might say, well, what is there to discover beyond the planets? And that's what that was our job, was to discover what was beyond the planets. The sun, the wind of the atmosphere of the sun expands supersonically, 1,000,000 miles per hour, creating a huge bubble around all of the planets that is called the heliosphere. And inside that bubble, it's filled with the wind from the sun, which is a plasma because it's ionized, and that plasma carries out from the sun's magnetic field, and that fills this bubble. Outside the bubble, the plasma comes from the explosion of other giant stars millions of years ago, and that plasma carries with it the magnetic field of the galaxy. So that's what's inside, and we are now outside. If I could have the first slide, this is a Hubble image of one of these astrospheres around a nearby star in the Orion Nebula. And you'll notice you can't see the astrosphere itself. You see the star brightly shining with an orange bow shock around it, but you can't see the object, which is a large invisible sphere. What you see is a shock created as the interstellar wind comes from the right side of that image and is diverted around the bubble that you cannot see. And it glows because it's been excited by that whole process. We're inside of a bubble like that and are now out in that bright orangish, yellowish region out in front of our own bubble. Now, if I could have the video, please. Turns out that Voyager's been on its way for 35 years, 36 years now. It travels outward at 1,000,000 miles every day, almost 1,000,000 miles a day. And it was 2004, 9 billion miles from the sun, before it had any sense of being close to the edge of the heliosphere. That's when it found that the solar wind itself had slowed down from supersonic to subsonic speeds. And in this picture you see, the blue area is the heliosphere, the darker blue is the supersonic part of the wind. And Voyager 1 crossed into the layer that's beyond that, the blue or somewhat darker blue area, in December of 2004, 9 billion miles from the sun. It was another 4 billion miles before it reached the edge of the bubble, and that was in August 2012. That's when we saw the energetic particles inside the bubble leak out and disappear, and that's where we saw for the first time the lowest energy galactic cosmic rays, which are in the space outside, where suddenly could be seen. And from that point of view, it looked as though we had crossed into interstellar space, but we did not, in fact, we're not able to conclude that. You might say, why didn't we know in August last year that, in fact, we crossed into interstellar space? That's because the boundary really is the boundary between these two plasmas, the solar plasma, the wind, and the interstellar plasma. And unfortunately, our plasma instrument does not work on Voyager 1. So we could not directly measure these two plasmas. So we used a proxy, and that proxy is the magnetic field carried by the two plasmas. The field carried by the sun is directed like this. The field we thought carried by the interstellar wind was like this. So we thought when we crossed the boundary, we would see the field rotate. Well, we crossed the boundary, and that's what happened. No change in direction, just an increased strength of the field. So we couldn't conclude that, in fact, we had changed plasma environments. We couldn't directly test that idea. So what do we know now that we didn't know a year ago? Well, we were very fortunate that the spacecraft has on it, besides the magnetometer, which is what we used as a proxy, we also have these two 10-meter antennas, which are part of the plasma wave science instrument that Don will talk about in a moment. And that was very important because it gave us another way to measure the plasma, assuming there were some waves in the plasma. The last time, though, that instrument saw any waves was when we crossed that termination shock at the 9 billion miles. There hadn't been a wave for another 7 years, until the sun basically had an eruption in March of 2012, which was fortunately headed in the direction of Voyager. In about 400 days, like a tsunami, it finally got to where Voyager is. It caused the plasma to react in a way that it could be sensed, and we knew for the first time we were in the dense plasma of interstellar space, not in the rarer plasma of the outer part of the solar envelope. So that's a major new piece of data, and I think it convinced most of us, at least, that we indeed are in interstellar space for the first time. So that was a lucky gift from the sun, and we hope that there will be more such eruptions so that we can measure the plasma as we continue. Now, what does it mean to reach interstellar space? Well, first of all, it's just, we got there. I mean, this is something we all hoped when we started on this 40 years ago that this would happen, but none of us knew how big this bubble was, and none of us knew anything could last as long as the two Voyager spacecraft. So certainly luck is an important part of this, but wow, when we first saw that data a year ago, it was really quite stunning after having been on the way for so many years. This remarkable journey is clearly a tribute to the many individuals responsible for the success of the Voyager mission over the last 4 decades. In leaving the heliosphere and setting sail in the cosmic seas between the stars, Voyager has joined the other historic journeys of exploration, such as the first circumnavigation of the Earth and the first footprint on the Moon. This historic step is even more exciting because it marks the beginning of a new era of exploration for Voyager, the exploration of the space between the stars. So I'll turn it over to Don.
Thanks a lot, Ed, for the introduction and for commenting on the plasma wave instrument. Well, as Ed said, the real issue here is plasmas. Which kind of plasma are we in? Are we in the solar plasma or the interstellar plasma? Now, it's just an unfortunate thing that the instrument that was designed to measure plasmas failed a long time ago, about 1980. Now, the instrument that I'm responsible for, the plasma wave instrument, it's designed to measure waves propagating in this ionized media out there we call plasma. It's kind of an exotic subject, but there's a lot of different types of waves propagate. Some that are just like sound waves, like I'm talking with here. They're called ion sound waves. They propagate sometimes great distances. They're also radio waves. Now, our instrument consists of 2 long electric antennas. If you bring up the picture of Voyager, you can see them there. They're 10 meters long. And we essentially have a radio receiver at the base of those antennas. I might comment those antennas are kind of like the V-shaped antennas you used to have sitting on top of your TV, you know, the rabbit ears. We can detect radio emissions. Jupiter, Saturn, and these outer planets are very intense radio emitters, and we've done a lot of research on radio emissions. But as I said, you can also detect waves propagating in the plasma. Now, there's one type of wave that's particularly important for us. It's called an electron plasma oscillation. You'll have an exam afterwards. I'll quiz you on the properties of this. If you displace the electrons from the ions and release them, there's an attractive force, and the electrons will proceed to oscillate back and forth at a characteristic frequency that we call the electron plasma frequency. It turns out this oscillation frequency is directly related to the plasma density, the number of particles, say, per cubic meter. And that's a very important quantity to try to distinguish between the interstellar plasma and the solar plasma, because it turns out, for reasons I'll try to explain shortly, the interstellar plasma is actually has considerably higher density than the solar plasma. So we can detect these waves when an oscillation occurs, kind of like a vibration in the plasma. But unfortunately, we don't do it all the time. And I'll get into why. For example, when we saw the cosmic ray changes, unfortunately, we didn't have any plasma oscillations, so we couldn't tell you the density. Now, okay, so when can we measure the plasma oscillations? Well, it's got to do with the presence of an electron beam. You know, it's like in a wind instrument. If you got air blowing in a wind instrument, you sometimes get a distinct pitch or sound, sort of like that. Okay, where do we get electron beams? We get those from solar events. Big explosions on the sun that eject plasma out from the sun, called coronal mass ejections, and you can run the SOHO image there. It'll show some examples. SOHO image, I hope it's running. Anyway, these ejections come out at very high velocities, over 1 million miles an hour. And sometimes they're very dense. A blast of plasma coming out from the sun propagates great distances. Takes almost a year to get out to Voyager distances. Ahead of those blast waves, electrons are accelerated at the shock that's in front of them, and they stimulate our plasma oscillations. Now, it turned out after the cosmic ray change, about a month and a half later, in October, November 2012, we detected plasma oscillations. And it was created by a solar event that, frankly, we're still trying to study exactly what event it was. It's sort of hard over such great distances to make those connections. Then there was another event in this year in April, May that was even stronger. Now, I'm going to show you shortly a spectrogram, a plot of frequency versus time. And on that spectrogram, these oscillations that I'm talking about occur at audio frequencies. So with our receiver, we can actually transmit them back to the ground. Actually, what happens is it gets stored in the spacecraft tape recorder, which we play back every 6 months. So there's some big time delays involved here. That's one of the reasons we're a little late reporting this. But we can play it back, and then you can actually listen to it. So what I'm going to do is start this recording, not yet, however. And you'll see a cursor moving. I have a 7-month interval that I show there that we compressed, fortunately, to 15 seconds. We aren't going to sit here and listen for 7 months to these things. But what you'll hear the first October, November 2012 event, and then there'll be a little bit of a gap where you don't hear anything. Then you'll hear the April, May 2013 event. So when you hear this recording, please recognize it's a historic event. It's the first time that we've ever made a recording of sounds in interstellar space. So play the recording. Sounds, as I tried to explain, from the frequency, we can compute very accurately the plasma density. And it turned out to be about 100,000 per cubic meter, just almost exactly what we expected in the interstellar plasma. In fact, when we saw the first event, myself, my colleague Bill Kurth, we said we're in the interstellar plasma. Now, you'll notice another thing in that recording. The frequency was increasing. Let's play it again. I put a dashed line on the spectrogram so you can kind of get an idea how it's increasing. So play the second recording. So this is evidence that where the spacecraft is moving into what I term a density ramp, a slowly increasing plasma density. And my colleague over here, Gary Zank, will shortly, but not right now, explain that ramp. I'll have to tell you that we made radio detections of the heliopause 20 years ago, in 1993. And I detected that same ramp as a shock wave propagated into the interstellar medium and the radio frequency, which is at the plasma, the same frequency, gradually rose. And those two observations seem to match almost perfectly. Well, let me go in a little more into what all this means. If you'll show the next illustration, this is actually one of Gary Zank's illustrations. And it shows there the sort of bullet-shaped heliopause. And inside the heliopause is that hot plasma from solar wind that flows out from the sun. And the very hottest part is out there where it shows red. In that region, the temperature is on the order of 1 million degrees or even several million degrees, extremely hot. And then the heliopause occurs, and then the blue region is the interstellar plasma. And in the interstellar plasma, we have various reasons to think the temperature is more modest, still high by terrestrial standards, but about 6,000 degrees. So you have this tremendous temperature difference across the heliopause. And to balance the pressure at the heliopause, you have to have a corresponding increase in the plasma density. The density has to go up when you go into the interstellar plasma. That may seem counterintuitive. You might think the interstellar, plasma it's like a vacuum, but it's not. The density actually goes up substantially. And as I described, we just measured the density on the interstellar side. If you go to the next slide, I show a plot of the plasma density as you come out from the sun on the left. And the red area is the very hot gas from the sun. And on the right is the interstellar plasma, which I colored blue because it's cool. And you'll notice right at the heliopause, there's that very large jump, which has got to do with the temperature differences. Now, we've actually measured the plasma density on the solar side at the termination shock, like Ed said, 9 years ago. We detected plasma oscillations at the shock. We often detect a lot of waves at the shock wave. And the frequency there was 300 hertz, much lower than the frequency we're talking about now. And I forgot to tell you, but density goes as the frequency squared. That's going to be part of the quiz I'll give you. And so since the frequency went up a factor of 10, that meant the density went up a factor of 100. So there's this huge density jump across the heliopause. In fact, by extrapolating our measurements, we make an argument in our paper that density jump actually occurred on or around August 25th, where the cosmic rays occur. So that's probably where we entered into what I will call interstellar space. Anyway, a very exciting time for me. I've worked, I've been working in space research for 55 years. I started working with Jim Van Allen. Incidentally, Jim Van Allen was very interested in reaching the heliopause with Pioneers 10 and 11, but unfortunately the spacecraft stopped operating first, and he died several years ago. I think he'd be very proud to hear of this event, and maybe he's actually listening. I'll introduce Gary Zank, my colleague here.
Well, thanks, Don. That was just the news when Don first called me. This was a little before the paper was quite extraordinary. He, I think, called me to sound me out a little bit about some of the models that we were developing, and he told me that the plasma frequency had suggested that the number density, the plasma density that they were measuring, was on the order of about 0.08 particles per cubic centimeter. And I think it took us both, all of 10 seconds, 15 seconds to conclude that we had to be in the interstellar medium. And so why did we conclude that? I think if we pull up the first figure, there's a simulation. This looks quite simple, but it comes from an extraordinarily complex set of simulations that we run on a lot of the sort of top-end supercomputers around the country. But what you can see in that blue side is the interstellar medium region. And you'll notice on the left side is white, and the white, in fact, is the solar material, the material that came from the sun. And these computer simulations illustrate very, very clearly that there should be an enormous jump in going from the solar side to the interstellar side in the density of the plasma. That plasma jump, in fact, is on the order of 100 times. Now, you might ask why, in fact, was the instrument not observing something that could have been in the solar medium instead of the interstellar medium? For example, these very strong tsunami-like shocks that Ed referred to. Well, we've examined that, and we know from the simulations and from the expectations of the underlying theory that, in fact, such huge enhancements of the number density are impossible to get within the solar medium. It has to be that we crossed over the interstellar medium. The other thing that you'll notice interestingly about that figure is that, in fact, although it looks very steep, that line that jumps from the solar side to the interstellar side is, in fact, somewhat gradual. There is a ramp there, and that ramp gradually increases, and so that again is very consistent with the kind of observations that Don is reporting. So that transition is called the heliopause, as Don indicated, and it has this 100-fold increase, and so consequently, because there's no other possible explanation, I think we're forced and we're obliged to conclude that we are in fact in the interstellar medium. This is truly a remarkable achievement, I believe. It's very hard for us, as I said, to comprehend that the space age started 55 years ago, and in that period we've actually exited the solar system. We've exited the material that's created by the sun, and we're in a truly alien environment. The material in which Voyager finds itself is not created by the sun. It's created, in fact, by our neighboring stars, supernova remnants, and so forth. And so Voyager, in some very real sense, is material that's not from the medium in which it finds itself. So we've truly crossed over. Nonetheless, Voyager has and continues, and I expect it will continue to do so, has a remarkable capacity to surprise. And so even though in some sense the observations that Voyager has presented us with in terms of the density and also in terms of the anomalous and galactic cosmic rays, those are all consistent with our expectations theoretically, it turns out that the magnetic field, as Ed alluded to, is still something that puzzles us considerably. And if we go to the next slide, our expectations were that the interstellar medium had a magnetic field that was oriented in a certain direction, and the interplanetary magnetic field, which is effectively like a big Archimedean spiral, meant that the orientation between the magnetic field on the solar side and the orientation of the magnetic field on the interstellar side would be somewhat significantly different, possibly by as much as about 30 degrees. And there would most likely be an increase or a significant change in the magnetic field strength. Well, what Voyager saw is illustrated on the right of that figure. You can see the little red and the little green and the little sort of lighter colored green curve. And in fact, there was almost no change, very little change at all. And so this is a real puzzle as to what is happening, what is the physics that underlies this absence of sudden change in the magnetic field. And the reason why this is so puzzling is if we go to the next slide, there's a series of three figures. The top figure is observations that were obtained by the IBEX spacecraft, the Interstellar Boundary Explorer. And what it shows is, in a sense, messengers and very energetic particles that are created, neutral particles that are created in the boundaries of this region that come to us and are measured by the spacecraft at 1 astronomical unit. And the surprise in these observations was there was this so-called ribbon, that region of green enhancement that you see in the figure. That was completely unexpected. We managed to explain it, or at least we thought we had managed to explain it, by creating a model that essentially relied very strongly on a certain orientation and strength of the interstellar magnetic field. And when we used this orientation and we ran these big computer simulations and we incorporated this additional physics, what we obtained was that figure on the lower left. And you can see that, in fact, theoretically, it does an excellent job of agreeing with the Voyager, with the IBEX observed ribbon. Unfortunately, if you change that magnetic field around and change its orientation and even its strength, you end up with something that looks more like the bottom panel on the right, which is a ribbon that doesn't agree with the observations at all. So we have now two constraints. One is we're in the interstellar medium. Voyager has told us that. The interstellar plasma density is significantly high, and there's almost no other conclusion that we can come to. And on the other hand, we have a magnetic field that can explain IBEX observations, and we have no theory whatsoever to bridge this gap. So we're in the fortunate position, I'm not sure if Ed and Don agree, but we're in the fortunate position of having another good few years of trying to explain this and trying to persuade people that they need to continue giving us a lot of computer time and money and effort to allow us to figure out just exactly what is going on. And in a sense, this is only really the beginning. Voyager, as I said, has this rather remarkable capacity to surprise at every turn. And we're now going into a completely new environment. It's truly alien. It's not part of the solar system. We've stepped into the galaxy. We're out of our solar environment. And what Voyager is going to discover truly beggars the imagination. I think that, at least for theorists, we've got 10, 20, 30 years of great fun and excitement ahead of us. And I'm looking forward to it. For me, just to end on a personal note, it's been truly remarkable. I was in high school in a different country altogether when Voyager was launched. I did not know of Ed, I did not know Don. It's been a privilege to get to know both of them, of course. But Voyager has had this capacity not only to do fantastic, really groundbreaking and remarkable science that is as Ed described, ranks with the greatest voyages of discovery of humankind, but it's also bridged generations of scientists across. And as I said, this is a mission that's almost as long as the space age itself, and I've had the opportunity of witnessing, in a sense, the launch, and now being at what to me is a culturally and historically changing moment in humankind. We've put something into interstellar space. It's our first step into the galaxy, and for a younger person, my daughters tell me not that I'm not a young person anymore, but for a younger person in any event, it's quite humbling to be part of this. So Suzanne, you're going to tell me why an obsolete piece of equipment still continues to function.
Yeah, thank you, Gary. Well, I'm thrilled to be here. Wow, that's about all I can say. I'll admit, like Gary, I was in high school when Voyager was launched, and I was a little more concerned about getting my driver's license than I was about watching Voyager launch at the time. But I'm excited to be here and talk to you today as the project manager. And the key point I want to make is that this mission is not over. I think you've heard all of my previous speakers tell you how much more science is out there yet to come. And many, many more discoveries are out there yet to come as well. If we can roll the first graphic. So Voyager was launched at a time where it could take advantage of a unique trajectory, which happens only 176 years. It could reach all the outer planets in a 12-year time period. The last time that could have happened was during Thomas Jefferson's administration. So Voyager 1 went by Jupiter and Saturn. That was the original mission. And then Voyager 2 was able to continue on to Uranus and Neptune. Between the two Voyager spacecraft, they discovered 23 moons of the outer giant planets. And today, Voyager is traveling away from us in interstellar space at over 38,000 miles per hour. Now, the Voyager spacecraft is old, and because of that, the science team who works on it are what we like to call well-seasoned. And if I can have the slide, the Team 1 slide. This is an image taken from 1972. It's the first Science Steering Group meeting held at the Jet Propulsion Laboratory right after the project was started. You could probably pick out Ed Stone. He's in the front row, the second from the left. His hair is a little darker, and he's looking pretty good as well as the rest of the science team there. And if I can have the next team picture, you'll see how we look today. Okay, so this image was taken on Monday, and it's nearly 40 years after the previous image. And this is the science team. There's about 12 engineers back at JPL who operate both spacecraft. And they've been with the project nearly as long as all the scientists. And what I can tell you about this group is that they are extremely passionate about their science. They are as passionate today. They argue, they banter at each other, they go back and forth at it in these science team meetings, and they're just as passionate today as they were in 1972. So one of the things I want to give you a sense for is the technology and the age of the Voyager spacecraft. So the Voyager spacecraft has only 68 kilobytes of memory on board. Now, I'm going to pull out my smartphone, which all of you have. Okay, this has 240,000 times more memory than the Voyager spacecraft. Okay, but it's the little spacecraft that could, we keep on going. We communicate with the spacecraft every day, both spacecraft every day, and we use the Deep Space Network that's run by NASA. And really, I would say the Voyager and the DSN have grown up together. The DSN has been with us the whole time. Voyager is currently 11.6 billion miles away from us. And the signal from Voyager to the Earth takes 17 hours and 22 minutes one way. Okay, Voyager transmits with a 22-watt transmitter. Okay, that's about the size of your refrigerator light bulb. Okay, when that signal comes down and the DSN picks it up, it's 1/10 of a billionth of a watt. Now, back in February, we were fortunate to have another observatory, the Very Long Baseline Array, which is operated by the National Radio Astronomy Observatory, try to look for Voyager's radio signal. Voyager was 11.5 billion miles away last February, and the VLBA went out there and looked for the signal. And if you can bring up the next graphic, they were able to see a blue speck, and this image represents the Voyager radio signal as seen by the world's most sensitive ground-based telescope. It's just a speck in amongst a sea of darkness. Now, I mentioned earlier that this mission can continue for several more years. We use radioisotope thermoelectric generators. They were provided by the Department of Energy. They decay at 4 watts per year. In other words, they lose 4 watts of power per year. So as a project manager and the engineers on Voyager, we have to be very careful to manage that power source so that we can continue to operate the instruments for as long as possible. And we have enough power to operate the fields and particles instruments, which are taking the current interstellar data out till the year 2020. So that's 7 more years we can operate these instruments. And then after the year 2020, we'll be turning off 1 instrument at a time until the year 2025, when all the instruments will go off. But that gives us a good 13, 14 more years to operate the Voyager spacecraft and get science data back from them. We can operate the spacecraft about 10 more years afterwards if we just want to take down engineering data. So where is Voyager going? Well, if we can have the next graphic, that's where Voyager is going. Okay, that star is AC plus 79, 38, 88. Voyager is on its way to a close approach with it in about 40,000 years. It's going to come within 1.7 light years of this star, and it will swing by it, and it will continue to orbit around the center of our Milky Way galaxy. And finally, I just want to comment that I really feel the people who had the vision to create Voyager, who built it and who sent it on its way, they just had an extraordinary vision about the discovery and the adventure. And Voyager was built for scientists, but it's really for all of us. Voyager contains on it, each Voyager has a gold record. This gold record was designed by Carl Sagan and his team. And on this gold record are music and greetings and sounds and even images of the planet Earth from all over the planet Earth. And it's really a time capsule of us. You know, this is us contained in this record. And now the Voyager, and particularly Voyager 1, is carrying this time capsule of us into interstellar space. And we're traveling along with Voyager as it continues on this journey of discovery. So, Dwayne, I'm going to give it back to you.
Thank you, Suzanne. Ladies and gentlemen, clearly an incredible team. And I want to acknowledge the Deputy Associate Administrator for Space Communications and Navigation, SCAN, Bondry Eunice, taking care and listening to the spacecraft. But I believe this team and all of the folks, many in this room, and listening to this program, let's give them a round of applause. Great job, Voyager team. Okay, here's how we're going to do this. We're going to go to the phone lines, but I want to let our folks out there watching, and I'm hearing in my ear there are a lot of you all out there buzzing about this news. Please stay with us because there is an incredible video that we're going to end the program with, so don't go away yet. We're going to go to the phone lines. We're going to take a few questions. A lot of the media around the world have their stories, and we want to thank Working with Science magazine and, of course, all of the work from Jet Propulsion Laboratory and again, the team. So let's go to the phone lines, and then we're going to take a couple of questions from social media, and then we're going to show the video. Let me take one question from social media. I think we want to try to go there first. There's my colleague, Jason Townsend, on the case, our manager for social media. Jason, what's going on out in the social media world?
Indeed, there's lots of buzz today all over social media about this announcement. So first question comes from Crow Robot. Has Voyager's path pretty well met expectations, or have unknown or unseen gravitational sources modified its course?
Its course is very accurately determined by the gravitational forces we're aware of.
Okay. Okay, now, we'll come back to social media. We're going to now go to the phone line. And I think we're going to San Francisco. David Perlman, San Francisco Chronicle. David?
Well, thanks very much for taking the call. For Don Gurnett, could you explain the results of the plasma oscillation in October and November 2012 and April, May 2013? And were they both the results of a CME from the sun, or what's all that about?
Yes, I can comment on that. The last event, the April-May 2013, we're pretty sure that it started with the St. Patrick's Day event, which was in March of 2012. I don't remember the exact dates, because the energetic particle instrument, Tom Kermegis' instrument, he's here, he could comment if you want, saw an effect there that had the right timing. Now, the other event, we've had more trouble identifying just what it was on the sun that produced that event. I think I'd have to say that's still under study, although there are some interesting things that have happened in the spacecraft that are not yet reported. I believe that's the way I'd put it.
I might comment that because the Earth moves around the sun, we are not always in the ideal position to see something headed toward Voyager. In fact, in December, we're on the opposite side of the sun from Voyager, so something from the sun heading out to Voyager we could not see from Earth.
Our next question is from Jackie Goddard from the Times of London. Jackie?
Hello, and congratulations. It's a question for Dr. Stone. At a teleconference like this last year, when you said that Voyager 1 was nearing the edge of the heliosphere, you said that you didn't know how you would celebrate when the moment finally came, but you knew that you would probably at least hold a meeting. Beyond just holding a meeting, how did you celebrate?
Well, we did hold a meeting. In fact, we've held 3 meetings since the plasma wave observations occurred, because this is obviously an exciting milestone for all of us. And I think we're looking forward to further meetings coming up with the American Geophysical Union meeting in December. So somewhere along the line, we will really celebrate. But individually, we're all overjoyed.
I might comment on that. Actually, I considered those meetings to be inquisitions.
Okay, now we have Bill Harwood, CBS News. Bill, greetings.
Hey, thank you very much. A question for Ed. What about Voyager 2? When would you expect it to get there, and what will it bring to the table instrument-wise that you didn't have with Voyager 1? Thanks.
Well, first of all, Voyager 1 is headed up toward the north and pretty much in the noseward direction. Voyager 2 is sort of down here in the south and somewhat off to the flank. So it's a different part of the heliosphere. And it's in sea, and we do have a working solar wind instrument, so we're actually measuring the plasma density, speed, and temperature. We will have that when we cross the heliopause on Voyager 2. In terms of timing, we don't know for sure, but it took 3 years more for Voyager 2 to find the termination shock on Voyager 1, so you might say another 3 years for Voyager 2 to find the heliopause to first order. But in fact, as usual, Voyager could surprise us.
Okay, next caller is Clara Moskowitz from Scientific American. Clara?
Yes, hi. Thanks for taking my call. I was hoping somebody could talk in a little bit more detail about the origin of the interstellar plasma, what it's made up of, and where we think it comes from.
Well, the interstellar plasma is created by the explosion of stars. So there's a stellar cycle where the interstellar medium collapses to make a new star. If it's so massive, that star has the life of only about 1 million years, and it blows up and puts all of its stuff back out into the interstellar medium. So the interstellar medium is constantly replenished by exploding stars. We do know there were a set of exploding stars near the Earth 5 to 10 to 15 million years ago, and the material we're currently surrounded by is stuff that came from those explosions plus what was there when they exploded.
Next question is from Kelly Beatty, Sky and Telescope. Kelly?
Yeah, thank you very much, and it's a great day. I'm a little confused by the timeline here. About a month ago, the article came out by Mark Swistak et al. That said that they thought that Voyager was in the in the interstellar medium, and Ed Stone came out with a statement saying, well, it's a little equivocal at this point, yet you had the plasma wave data at that point. So can you kind of walk me through the timeline of what you knew when you knew it?
Well, I think, Don, you should talk about the time it took to get the data down. Some of it was on the tape recorder in the spacecraft, and the time it took to really make sure this was plasma wave data and not radio data, right?
Yes, well, the data, the high resolution data we get, the type of thing that we played the sounds, they're stored on the spacecraft tape recorder, and it can be up to 6 months. They only play it back every 6 months. But I think I would also comment, or maybe Ed, you want to comment it. I believe the Swisdak paper was basically a theory paper, and as a matter of fact, our paper was submitted at least almost a month before theirs. They just got through the review cycle faster than we did. So if you want to talk about the timing, there are some of the factors.
Yeah.
Okay, we're going to take a couple more questions, then a couple more from social media, and we're going to try to close out at the top of the hour. But remember, stay tuned for that video. Mike Wall, space.com. Mike?
Well, yeah, hi, guys. Thanks again for actually doing this. And, yeah, a great job getting it out there. It's a big moment for all of us. I just had a quick question. Now that you're actually in interstellar space, what do you expect to sort of look for? What are some of the questions that you're going to be trying to answer out there? I mean, I know it's an entirely new environment, so it's tough to say for sure, but what are some of the things that you'll be looking for as this probe continues to send data back to Earth?
Don, why don't you start, and then Gary?
I can comment on that. Well, as I showed there, as Voyager is moving out, the density is slowly increasing. And, there could be various models for that. We saw a similar effect with the radio emission 20 years ago, and in that paper I described it as a pile-up effect, that the heliosphere is moving into the interstellar medium and that the plasma may, shall I say, pile up. In fact, there's a paper by Baranov that suggested that. For a simple explanation, I've been telling some of the media it's like a snowplow going through the snow and it piles up ahead. But I'm sure that there's more sophisticated explanations, and I actually know that Gary Zank has one. Would you like to take the ball now?
Well, I can certainly take the ball. I'm not going to continue your explanation or discussion further in that regard, Don, but to answer the question that was asked in part, there is a great deal of very interesting science that really opens up here. For one of the things I think that will be of tremendous interest and importance is to study more accurately the galactic cosmic rays. The galactic cosmic rays, of course, are created in the probably in supernova remnant driven shocks, and so in order to study those, we've always studied them from within the heliosphere, and that means studying the particles, these and very, very energetic galactic cosmic rays, when they're very strongly modulated by the presence of the solar wind. And so being outside the heliosphere allows us an opportunity to, in a sense, look at the undiluted galactic cosmic ray spectrum, the undiluted galactic cosmic rays. So that will tell us a great deal more about the interstellar medium at very distant locations. It'll tell us about how the galactic cosmic rays propagate through this very complicated interstellar medium. The interstellar medium is a mixture of hot, warm, ionized, partially ionized, not ionized gases, and And of course, it'll also allow us to study a great deal about the nature of the fluctuations in the magnetic field in the interstellar medium. And so already, in some respects, I believe Voyager is probably, and Tom Krumijis has reported on this, showing up a number of surprises in the nature of the galactic and anomalous cosmic rays. The anomalous cosmic rays, of course, disappeared, but where did they disappear to, and what effect have they on the local interstellar medium? So that's going to be a very large area of study. Another very interesting area that is worth looking at closely is, certainly we're in the interstellar medium, but the interstellar medium is itself affected by the solar wind and its properties. And so there are very complicated processes that lead to the deposition of momentum and energy into the very local environment, the very local interstellar environment. And one example is the propagation of the shock waves that were driven off by the sun into the interstellar medium. How do those propagate? What do they look like? What is the nature of the energy and momentum transfer from the sun to the interstellar medium? There are other processes at work associated with the deposition of energetic neutral atoms into the local interstellar medium, and that has a tangible effect on the nature of the interstellar medium. So all of that needs to be considered and explored. And then, of course, there's just the very basic questions of what is the nature of the interstellar plasma, proton, and electron distribution functions, and how do those differ from the solar wind? We unfortunately can't get at composition, but we can learn an enormous amount about the interstellar medium that we previously only understood from looking at using remote observations that are typically integrated over many parsecs. So for the first time, we're actually going to be able to put our hands into the interstellar medium and look at the stuff and ask what it does and what characteristics it possesses. So to my mind, it may even be more exciting than we've been through in the past 20 years, if that's possible. But it's going to be it's a tremendous opportunity.
Okay, we're getting close to the top of the hour. We're going to go to social media, and we'll take one more. And I believe you have another social media event happening later on this afternoon. You may want to share that, Jason.
Indeed. This question comes from Twitter user Jason Major. Will Voyager ever be able to take a picture of our sun or solar system from beyond the heliosphere?
We took a portrait of the solar system with Voyager 1 in 1990. And after that, we unloaded the software on the spacecraft to run the cameras. And we no longer have the computers, which are quite old by now, on the ground to process the data. And as our power supply has gotten smaller and smaller, we would not have enough power to turn those instruments back on at this point. So no, we cannot provide any more images.
Wonderful. Thanks for answering a few social media questions. For everybody on social media, if you are on the platform Reddit, later today, we are going to be having a bunch of our scientists up and talking and answering questions in an AMA on Reddit. That's an Ask Me Anything. So if you look on the subreddit on there for an Ask Me Anything thread, we'll be there later. It's reddit.com.
Thank you, Jason. So ladies and gentlemen, clearly, we want to thank you for being here. Before we get to the video, a couple of notes here. Again, all of this information and more is available on www.nasa.gov/Voyager. And our social media, as Jason said, is deeply abuzz on what's going on. So let me set up this video for you. Very cool. Over the past several months, folks were asked what message they would send to Voyager to commemorate its arrival in interstellar space. What you're going to see are some of those messages. You know, when Dr. Grunsfeld was up here, that Star Trek context, the audio was low here, but he created quite a buzz when the Star Trek theme was playing while he was talking, so check the internet for that. But you will recognize faces here from Star Trek and from other places. And I think, John, me being a Trekkie, and I think they're Trekkies, and I know you Trekkies out there, if Mr. Spock was here, he would say something like, fascinating. Thanks for joining us, and enjoy the video. Thank you for joining us on this historic moment.
There's Voyager crossing over into interstellar space. It's the farthest thing we've ever sent anywhere.
Voyager accomplished its mission so brilliantly, and now goes on.
This vehicle, which is long past its expected service life, is still sending messages.
They're going beyond what we know in our neighborhood.
We are boldly going where no one has gone before. It's as simple as that. This is awesome.
The Voyager record, and really the Voyager mission, were conceived and executed on behalf of all humankind.
With the sounds and heartbeats and whale sounds and all the different languages of the world.
Hello from the children of planet Earth.
My name is Nick Sagan. I'm the son of Carl Sagan, and in the 70s I recorded Hello from the Children of Planet Earth for the Voyager Golden Record. Dad would be enormously proud. It would be a great celebration. It's an amazing accomplishment.
Paz e felicidade a todos.
I was selected to do Portuguese. It's hard to imagine aliens being able to decipher the Golden Record, but if they can decipher it, I like to think that they'll take our message in a positive spirit.
So we stand today at the threshold of a great epoch of infinite potential for discovery and exploration.
This is not science fiction. This is better than science fiction. This is science reality.
So Voyager, I bid you farewell.
And thank you for being our ambassador. Job well done.
You should write. You should maybe drop a postcard. Let us know how you're doing so we shouldn't worry.
Congratulations to everyone on the Voyager team.
But don't stop there. Many more worlds to explore.
And thank you for expanding humankind's universe from Earth to interstellar space.